Yo, hello. Today I will play my 10 million TNT Minecraft clone. This is it. It's using C++, and also we will look at the video, my very short video that documented the project, and we will watch the journal playing my project. So this will be a very exciting stream. So let's start. Um, let's first look at the video showcasing the project, then the journal, then we'll play it uh, here, and I may go through some interesting parts through the code. So let's get started. One cool part is this music comes from Good Kid Band. They reached out to me. This music released at the moment I uploaded the video. This was very cool moment for me. For exploding a lot of TNTs, they are on YouTube videos. Um, Exploding lots of TNTs. Minecraft TNT explosions. There are many videos, and do you know how they managed to do all of this? Like this guy blowing up TNT without luck, or this guy, this guy. They blow up lots of TNT seemingly without any luck. And here they have like 16 million TNT. And you watch this and you're like, how is this possible? Oh, come on, explode it already. Okay, this is realistic. Look at how slow it is. Yeah, this is realistic, but this is different. This should be different. Did you see how many TNT there were? And there was no luck. And basically, how they do it is they install a mod that runs the game way slower, so that there isn't any luck. And basically, you have footage that's many hours and you compress it down to a few seconds. That's how you get it, and I demonstrated here in the video. Like this is the actual how slow it is, and then I show it sped up. Do you notice the difference? Here I'm demonstrating that I've changed entirely how the TNT works. That's how I removed the lag. Sorry. When a TNT explodes, in my code, it changes all the cells, their information. So when a TNT lands on that particular cell, like here I demonstrated with the glass, when a TNT now lands, for example, on this block where it's near the explosion, it will automatically know where to go from there. This simplifies the explosions a lot. Here I'm demonstrating how I've made it possible to really fast update the terrain, because usually when I have to go through every chunk and draw each chunk, like CPU communicates with GPU, etc. But here, everything lives inside of the GPU. All the data is directly in the GPU. So that's how it's a lot faster for the updates of the terrain, because I can easily simplify the TNTs to make them explode more easily, but they have to do lots of updates to the terrain, and I have to visualize this, because when you render a terrain, you have to go through every block, and for each block to calculate the vertices, then to send all of that data to the GPU, and then to be able to render it. So this was a big problem I had to solve, and my solution was to have everything to live in the GPU. And here, because all the data is in the GPU, the RAM is only 40 megabytes. But the GPU memory used was gigabytes. So it's a trade-off. If your GPU doesn't have enough memory, it will struggle. Here I added support for texture packs so that I'm able to give out this project to everyone, and that's how we have it as a GitHub page where everybody can download and run it and even look at the code. And because of this, I was able to send the project to the Cherno who reviewed it, which we will watch later. Here I combined many different texture packs. This Painterly texture pack is super old school. And I had some modern texture packs, and I had to combine all of those together to be supported through my engine, which was almost impossible because some texture packs have one type of data, other texture packs have other type of data, so I had to support all of that so we can have different kinds of textures. That was really annoying. I should have stuck with just one Minecraft version texture pack. And here I'm showing how you draw one simple cube usually, but I did it differently because when you use Unity, a game engine, you just expect the object to be drawn. You don't think about it how it's actually drawn. Everything is drawn with primitives, and usually the primitive is triangles. But since I'm not using a game engine like Unity and Unreal, I can change that primitive. And I changed the primitive, which allowed me to drastically lower the data used. Yeah, here instead of triangles, I use triangle strips. Triangle strips. Yeah, like this. So with triangle strips, you just say like you give this vertex, and this vertex, and it automatically creates the triangle. So as of now, it's 3 vertices for a triangle. Nothing has changed. But then you just give one more vertex, and it automatically uses the previous ones to create another triangle. So you can make the cube with a lot less vertices, which lowered the used memory, the memory that was needed to handle, because I have to generate for each block the needed vertices. It drastically lowered the needed memory, which was important since we're working with 10 million TNT. And here, like when you want to render the same mesh multiple times, use instancing. Instancing will allow you, when with one draw call, to render lots uh, lots of copies of the same mesh. But the issue was that um, no matter how many of them are visible, the FPS was the same. This was important for me to solve because some of the I don't have all the TNTs at the same time working. Just some of them are as entities, and so I can take advantage of that and to have more FPS. But here I show how when I have not when some of the here I just show that when TNTs explode, the FPS doesn't improve, and then I show my solution. And here notice how now with my solution, when the TNTs are gone, we have a lot more FPS, and this was achieved using geometry shader because doing it like that, I just the geometry shader allowed me inside of the shader to decide, are we going to actually render the TNT, because at the previous point the TNTs were just invisible, but still they had a cost, even though there was I was just making them invisible. But with geometry shader, I can actually like remove them. And all of this was possible because of the Cherno. I learned OpenGL through his videos, and he actually reviewed my project. So now we're going to look at his review of my project.
Buckle in, boys, we got a good one. Hi, Cherno. I started learning OpenGL seriously 10 months ago using your OpenGL and Game Engine playlists on YouTube. Wow, those are old. Here is a GitHub link to the source code. We'll have that link in the description below in case you guys want to check it out. The project is a Minecraft clone with 10 million TNT. That's the title of this email, by the way. The project is a Minecraft clone with 10 million TNT that you can explode by going near a TNT and activating it with the left mouse button. Sounds like Minecraft. I cloned the repo from my old laptop to make sure the process is without problems. This is what I love to see. This guy has tested his code before sending it in for a code review. Why everyone doesn't do that is beyond me, because
I tested my code, so I'm certain it can run for him without issues. Is because I looked at his, I have watched his all his other code review videos, and it was really annoying, even as the viewer, to see that the project doesn't run. And I had a specific goal, like I will do everything in my power to make sure it runs without issues for him, and I managed to achieve that. And I achieved that by running the cloning the project, the repo in my laptop, and inside of my laptop I tried to run it, and it didn't run. I found many issues. I solved all of those issues, and it was worth it because now it runs for the journal without issue.
Because half the time nothing works. I haven't seen the code yet, but I already like this guy. Interesting points. Wow, there's a lot of information in this email. The project mainly uses compute shaders. That's cool. To render the TNT entities, I do one draw call of 10 million points. Okay, then a geometry shader checks if the entity represented by the point is visible. If it is transformed to a cube using 14 vertices, else no point is drawn. 14 vertices. I wonder why 14 vertices. I learned about geometry shaders from the book OpenGL Super Bible. Oh, that's cool. I remember reading that book when I was like first getting into this kind of stuff. The world data is stored in shader storage buffer objects. For the train, I'm using vertex pooling where I pack one side of a cube in a single entity. This is a really cool project so far. From there, using GL multi-draw arrays in direct, where one draw is one chunk. The shader goes through the array of ints for the current chunk. The TNT explosions are simplified with a BFS, like a breadth first search, I expect that means, that traverses in the same way as when the light spreads when placing a torch. This way, each TNT entity can independently check only the block it is in. If that block has an explosion level, like the light level from a torch, it quickly finds the ID of the entity that caused it, and based on the position, it calculates to what direction to be blown to. The cool thing about the BFS is that I couldn't find queues for GLSL, so I had to use an array as an alternative.
Okay, for this part, like the most important part for having so much FPS blowing up the TNTs is I was inspired by how torches work in Minecraft. When you place a torch in Minecraft, it goes to neighboring blocks and it changes the light level. And in my mind, I got inspired from that and made it possible where when a TNT explodes, it changes an explosion level instead of a light level, because the lighting system in Minecraft is very efficient, and I use the same system but for exploding TNT. When a TNT explodes, it changes the so-called explosion level. I want to play the clone, but you have to be specific which clone. This is the third Minecraft clone.
Okay, I don't know exactly what this means, but
here, what I meant was the cool thing about the BFS is that I couldn't find queues for GLSL. What I meant here is that when you work with shaders, you don't have like data structures like a queue, and when you look at like BFS implementation, they usually use like a queue, like some kind of a data structure, and inside of here, in the shaders, when you because what my Minecraft clone here uses compute shaders for maximum efficiency, I don't have such data structures in the shaders. That's what I meant. Here I have a shader, and in here inside of the shader, which uses GLSL, you don't have any data structures like a queue, and I had to use an array to implement my own queue. That was fun.
maybe we'll find out. Like, are they literally talking about like a queue data structure? Because that's a bit weird, but I don't know. For the CPU to know which chunks to redraw and how many visible quads it has, I've set up a persistent map that I can easily reuse. I learned about them from the GDC video approaching Zero Drive Over. I remember that in OpenGL from GDC Vault. How old is that? That's like Very old, isn't it? I feel like this is a classic, this video. Yeah, GDC 2014. Damn, that's cool. This is a blast from the past. It was surprising how much synchronization needs to happen between everything. For example, after the quads are generated from a compute shader, I had to do a GL client wait sync because otherwise some parts of the train end up missing. Okay, that is probably an error on your part because I don't think we should be really doing anything like that. When it comes to like compute shaders, because most of this is done within compute shaders, I'm expecting that there's probably indirect draws that's actually contributing to rendering this. Yeah, I mean, like when it comes to CPU GPU synchronization and extreme sync points like this, so this function we might explore this a little bit in more detail later. Actually, to be honest, this whole project, the way that I'm seeing this looks really deep. This looks really kind of like it could be a lot to get through, like a lot of content, but it's like, I mean, I haven't seen much of it yet. Let's see if there are some screenshots. Okay, yeah, I mean, this is pretty much what I expected.
The craziest part about this project, this project was so much work. It was so exciting. It was so cool. But then if you look at like my channel, when I made a video about it, here, blazing fast GPU compute, 10 million TNT explosion, like 14,000 views. And then I make a video like making a Minecraft clone in Unity, 16,000 views. This just didn't make any sense. Like, this project was so much work. It was so cool. It had so many. I think I just didn't. It was on my part the issue. I probably didn't showcase properly the project.
Okay, cool. And then I guess it runs like for 10 million. This is probably like a tower or a cube of like 10 million TNTs. Oh, there's a video. Let's take a look at the video. Okay, so we have 1,000. We have 10,000. Objects are usually drawn with triangles as a primitive. So this is probably the geometry shader that would assemble it into that from points. And then 10 million TNT with one draw call using instancing. Ah, here it is, 10 million. Wow. Okay, so we've got like 30 FPS or so, 20, 19 FPS is falling, but wow, 10 million TNT, that's cool. I mean, I've never tried to do anything like that. I could see it, I could see it being quite possible. Yeah, wow, that's really cool. Oh, that could really do with some ambient occlusion. It's very hard to tell what's going on here. Yeah, what a cool project. There's some more information here as to how explosions are handled. So each chunk has a 3D array of ints. Yeah, I mean, I think it'll probably be more fun to actually explore the code, but it's cool that there's like so much documentation here in the email as well. For this code review, I did my best to do some abstractions and clean it up, but that's where I struggle. Okay, so abstractions and cleaning it seems to be a struggle. When building a big project, what advice do you have for organizing and abstracting the code? So we can talk about that. This is my 4th Minecraft clone, and I always start over because I quickly see the issues of my current implementation and have ideas on how to improve it. For example, in my past 3 clones, the engine and game were one project. Okay, the issue was when I started over, I had to start over the engine too, which now with the 4th one, it's not the case. Okay, so you're kind of building some kind of core library that you can reuse for all these different attempts, I guess, of building this project. It will be a full circle moment learning from you, OpenGL, and then seeing you review this project. Well, full circle moment complete. We live at a time where remote work is normal. Maybe you're half.
Here about the abstraction, my main issue was that like I always start over. That was my main issue, and the journal advised me to continue working on the same project until I reach some kind of end. And that's why I continued working on my where was it, the 300 plus hour clone, this clone, and I continued improving it, adding redstone, more redstone components. So I did follow his advice. And we have chats. Hello, hi, hello, hello, hello. Let's continue with the video. I think this is a sponsor.
For up to 5 users, and if you don't need any of these advanced features. So go to twingate.com, link will be in the description below, and give it a try today. Huge thank you to Twingate for sponsoring this video. Thank you for all the free and amazing content. Hopefully the OpenGL series gets continued. Nah, sorry, it's a bit too late for that. A frame buffer video would rock. Also, the latest series on building application with layers and events is really interesting. That's the architecture series. And helpful, I like the direction. Cool. Pika, Pekka, CS, you're very welcome. Thank you for sending in such a cool project. I feel like this is going to be the subject of a few videos. Again, I haven't looked at the code yet, but there seems to be a lot here to unpack. So if you guys watching are also interested in this project and you think you want to see more videos, definitely leave some comments below and I'll do my best. I think one thing that I can immediately say about this whole thing of what advice do you have for organizing and abstracting the code, this is my 4th attempt and I always start over. So on one hand, I think starting over is probably healthy. One thing that I actually used to do is, I remember when I was first learning programming, I was probably like 16, 17, I would come home from school and I feel like every night I remember sort of trying to make a game again from scratch. On one hand, you could argue like, why didn't I just continue writing that same game? I would have gotten further. I probably may have learnt more. But for some reason, when I kept like trying to do it again and again, that process, I think, of in a way iterating over that base set of code that I needed to write to get something to work, and this was like back in the Java days, that probably critically taught me that base layer, that base set of code that is the foundation of honestly any kind of project. And I think that was helpful. However, on the other side of this coin is the fact that if it's your 4th attempt of writing this Minecraft clone and you think that you keep having to start it over and you're not sure about how to organize and abstract the code, you might also just not be implementing the complete picture until you've sort of created a Minecraft clone fully, let's just say, for the first time. You don't really know what goes into it. And if you don't really know what goes into this system, this like technical project that you're creating, it's very hard to create an effective abstraction and organize the code because you're just not sure exactly what you'll need in the future. And until you have that full big picture, how can you possibly architect something that's going to work going forward? I think based on what I've seen here, my advice to you might be to just push through this desire to organize and abstract the code and actually get the product working. Get what you're trying to make working, at least to an extent where you're like, okay, this is like an MVP. This is my vertical slice, which demonstrates some kind of set of features or a milestone of this project. And
here what he says is like basically to not be making constantly so many Minecraft clones, to pick one clone and finish it, to have some finished state. And I did that. I continued working on it. This Minecraft clone, I continued working on it, and I managed to, and I'm glad I did it because I saw how important it is to be able to import JSON files, because here inside of resources, models, here you have all kinds of JSON files when you want to render something. For example, is there some complex JSON file? Yeah, like this complex JSON file. To be able to import the tripwire, you have to be able to render all of this. And I added the functionality for my project to be able to read all of this and to automatically render it. This was very, very important functionality to continue on with the Minecraft clone. And I didn't have that beforehand. And now I have it, and I managed to add it by finally just moving on, continuing. And the main issue with continuing with the project until you reach a final point instead of having so many Minecraft clones is that it becomes a big mess. It becomes a big mess because here I have like zombies. I was rendering zombies, and here the zombies, and they use my old rendering system where I had directly using viols, an array of quads. That's my old render system. I have inside of this project, since I'm just moving on and not starting over, I added on top of all of this mess a new render system using components. Here I have mesh filter component with a mesh class. This really helped me with abstracting away rendering. But the issue is, like, I still have my old render system, for example, for the zombies. Like, that's kind of an issue because it becomes a mess. And here, when I mentioned the JSON files, I added the functionality to be able to read and render JSON files. This was a major improvement, but the issue is that some blocks use this system. My old blocks that I implemented still use old rendering systems for drawing blocks. Like it was all manual. For example, for the cobblestone, this was all the code manually implemented. But for something newer like the tripwire, I'm directly here I'm directly reading from the JSON file. And another issue is that um, from all the mess of the code, when um, I have to wait it to start up so I can demonstrate to you. Is there an issue? It doesn't matter. Yeah, so basically there are a lot of negatives just pushing through. Like here, uh, when I was when I create here the icons for the items, this uses the old rendering system, and that's why most of the new items are just a dirt block. They don't have a model here. This piston has a model for the item because it's using the old code, the old code. I need to update this so that it uses new rendering. And here, because I changed the rendering system for the terrain, I still haven't updated the cobblestone and the other blocks to be part of this new rendering. So where I'm getting at is because that was my motivation to start a new Minecraft clone, because at some point it becomes a big mess. And I just didn't want to deal with this mess. I thought it would be better to just start over. But I sent my project to the Cherno, and he advised to not start over and to keep pushing through this mess. And that's what I did. And for now, as of now, I'm okay with that.
And what that gives you is the understanding, this first-hand knowledge of what it actually takes for this project to do what you need it to do. What you actually have to program your computer to physically do to make this result happen.
And the cool part, like from what the Cherno is saying, he is right. The cool part of pushing through all this mess is that if I start over now, I know what I should do from the start. Like I now know, and I'll get much farther if I start over now, but I'll hold on to that. So if I started over, I would have my new component system for rendering meshes. I would instantly start working on implementing to be able to read the JSON models for rendering all the blocks. I know what I need to do if I start over, but that has a big cost, and that's why I'll wait until I start over. I'll wait and push through this like mess of a project. So this advice he gave was really helpful to me.
Once you have that, you can think about architecture and you can think about organizing and abstracting the code into something that's going to be scalable for the future, maintainable, reusable into an engine, all of that sort of stuff. But if you just don't have that knowledge yet, I could definitely see you adding a feature or making a discovery and then being like, okay, well, I need to re-architect this whole thing because it didn't work with this preconceived notion that I had about how I maybe thought this would work. So yeah, maybe don't give up on your design quite so quickly, complete it to some extent, and then go back and refactor it and learn from it. Okay, so here I have it open in Visual Studio. We've got a release build. Let's run it. Let's see what it is. So as shown in the GitHub screenshots, I mean, we just have, this is immediately how it launches. So this looks like, sure, this is 10 million TNTs. Can we go inside them? Oh, this is so, yeah, I'm guessing they're all here. We've just got backface culling turned off, so it's a bit hard to see.
Here, what he expected was, I'll just start it. When he went inside, he expected to see all the individual TNT. But when they're like this, they're just static blocks, just like the terrain. That's why he didn't see everything inside. When they're separate entities, that's when you have all the individual TNTs. He expected to see each individual TNT, but this was just an optimization I made, and that's why he cannot see each individual TNT. When you activate the TNT, that's when they become an entity, and you can see all the unique TNTs. And this is just an optimization.
And then I'm guessing I can interact with any one of them by just clicking. Oh, yep, that's triggered that one. And then let's see what happens. Okay. Oh, there's sound. Whoa. Look at that. Okay. Performance is kind of falling a little bit. And then they're all, yeah, I mean, a lot of them are in the air. They'll just explode in the air and not affect everything. But we've also created this massive crater, which, as I mentioned earlier, really needs some ambient occlusion because it's really hard to see what's going on. That would improve the look of this dramatically. And yeah, and we've just got all these blocks here. I can click to remove them as well. So this is all fully editable. If I right click, I can't place blocks, I don't think. But yeah, I mean, that was pretty cool. And it did run quite well. So this is all implemented using compute shaders. So it's basically all happening on the GPU. I think it's going to be a really cool project for us to look at. So let's get into the code. Since the
Oh
author of this
no.
code did ask for my advice on architecture, organizing and abstracting the code, I think I'm going to focus more on that, just the general application, architecture, organization, abstraction of the code base that we have over here. And then in a later video, because I really want to, and I mean, if you really want me to, let me know in the comment section below. I'm going to take a look at the compute shaders and
There wasn't a later video. This video is like 4 months old. There wasn't another video.
the magic that actually makes all this happen and how that sort of works. So starting off with this, I can already see that we have two projects here aside from the dependencies. So we have a Minecraft clone and we have this voxel engine. Something else that I should probably point out as well is that inside this repository, we have generate projects.bat using premake. So this is the premake file. We've got debug release and dist. So this is very familiar. This looks exactly, actually, all of this code looks exactly like my game engine series / Hazel. So that's pretty cool. It's very, very familiar to me. We've got all three of those configurations here. Everything's being linked in to the voxel engine library, which is over here, and then that's in turn being linked into the actual executable. C++23 is the version of C++ we're using, which is pretty cool, nice and modern. And then yeah, we just have this application, this voxel engine application inside Minecraft clone.app. The relationship between these two is correct as well. So we have voxel engine being built as a static library. There it is. And then that's being linked into the actual executable, which is our game. Inside here, we have layers, again, very similar to both the game engine series and my architecture, my C++ application architecture series, which I'll have linked up there as well. All of this stuff looks very familiar to how I write C++ as well. On tick, I wonder what the difference is between on tick and on update. They're both taken.
On tick, I wanted to make it so I run all the calculations like in a capped FPS. So like when you run the game, your FPS is varies a lot. It can be like 10 FPS, then it can be like 200 FPS. And I wanted to limit all the complex calculations to be like 20 times per second, to not reach a point where they're like 100, 200 times per second to run all the complex calculations. I wanted to put a limit, but then I thought to myself, this limit is useless because when you have 10 million TNT and the FPS tanks to 10, this limit I set on tick is meaningless, because if I set a limit to run 20 times a second, but the whole game lags down to 10 times a second, like it was meaningless. But I forgot to remove it, or actually I did remove it, but he didn't get the newest version. He had made the video before I did some improvements, so he shouldn't look at on tick.
Time steps, so that's interesting. And then we have our main game layer, which I'm guessing is where basically everything happens. Yep, that's a lot of lines of code. Well, relatively to the other stuff we've looked at. And there's also a lot of OpenGL functions here. Okay, so this must be, I think this is the whole, I wanted to integrate this. I didn't abstract it and hard-coded it in the game where it's good to have no OpenGL code. So there's clearly some hesitation on.
Yeah, here I had issues with having OpenGL code directly in my Minecraft clone. because when I looked at his tutorials, he abstracted everything away inside of the engine. You didn't had any OpenGL code when making the actual game. Everything was abstracted, and I was feeling bad that I couldn't figure out how to abstract all of that.
How to maybe abstract OpenGL, which is fair enough. Oh, we got this profile scope, which again is very similar. Oh, okay, so we're using Tracy here, I expect. Got instrumentation timers. Oh, no, we're not using Tracy. We're using, this is my old JSON. Oh, I remember this. So this is this, I believe. So the
He's right that this is for profiling. This code that he shows from that he has written, it's so that you can see where in the code you have like issues, so you can improve that, make it more efficient to get more FPS. But I have his code in my project, but I'm not using it. I'm using Tracy, but I didn't remove his code. I started using his profiler, and then I moved to Tracy, and I haven't removed the code. But he mistakenly thinks I'm still using like his thing.
cherno/instrumenta.h is a little gist that I have over here. And that's where this code is coming from. So this is something that you can actually open up in Chrome tracing and then see. I made a video about this like years ago. How old is this? Okay, there's 2 revisions here. So that was in 2019. That's crazy. It's crazy to see people following the Game Engine series because that is such an old series. And then they're obviously doing kind of stuff that I did back then. Yeah, that's insane. What a different time it was back then, eh? Okay, so that's cool. But yes, I would definitely use something like Tracy instead. Oh, this is crazy. I'm actually really enjoying this project already just because it's sort of familiar to me. It almost feels like I wrote this because this is kind of how I would write this. I mean, especially back then, my style has obviously evolved, but the general architecture of this is my game engine series, basically. So that's really cool. And we've got source vendor over here. We've got the precompiled header. We've got this general sort of all-inclusive header, renderer, GUI, events, debug. So this is all of the actual core engine stuff we have. Yeah, even this like little Unity build of GUI files. Wow, this is just nostalgia to me. Okay, so let's kind of get back to the beginning here because I'm getting a little bit ahead of myself. So we have an application. We don't have that whole, I was going to say we don't have the entry point. We do have this entry point included. So this is, again, from my game engine series. We have a header file which actually includes this entry point. And the rationale behind that is also got this extern create application which needs to be supplied by the actual app. So the rationale is that the entry point is defined clearly and lives within the actual engine because the engine in a way should be controlling the way that the application starts up because it has to do so many things that are related to the core application. It's the engine actually running this stuff. So therefore it makes sense for the engine to define this entry point, but obviously the entry point has to exist within the executable within the application, which is why we include it over here. And then that code will physically get compiled as part of our exe and not our static library code. But then, because we want to control what sort of application we make, we mandate ourselves to basically include this create application function because this gets called from the main function, which is defined over here in this header file, which is part of the core engine, but you can see it's not implemented. So this is immediately.
When I first watched this video, I was like, this is already at minute 15, and he's spending so much time like on the main function, explaining the entry point functionality, how it works. And I was like, he will never be able to go through the entire project with this slow pace. And I was like, oh no. I wanted the video to go more in depth. That was quite a little bit disappointing, but he said he'll make other videos, so I'll just be waiting.
Going to give you a linking error unless you implement it somewhere. And the idea is you implement it over here inside the exe. And then all that application does is it pushes a layer, which is this game layer, into the application's layer stack. So application, probably not even going to look at this too much because this is going to be very similar to the game engine series and to even Hazel today is very similar to this. It's not quite the same, but it's similar enough that people would recognize this, I think. So yeah, this is all very familiar to me. I literally don't have to look at this code because I already know how it works and what it is. And then we have got these render commands as well, which is the beginning of an abstraction, which again is from the game engine series. Look, I mean, I have to say that in general, I'm not the biggest fan of this abstraction, even though I sort of created it in the game engine series. It might make sense for an API like OpenGL, but it's also very fine-grained and it wouldn't really translate well to Vulkan or DirectX. I can see perhaps why the author of this code struggled to also figure out how to abstract this stuff, because maybe it doesn't quite make sense. I mean, what they could have done is sort of looked at this render command and just kept adding render commands for the specific render API, which in this case, is there like a GL render API? No, not really. So render API is actually a class with these functions, and I think they're probably supposed to be virtual. Yeah, so I think in my original design, these would have all been sort of pure virtual.
His original design, he made the engine tutorial in a way where you are currently implementing the renderer with OpenGL, but you can easily switch to other renderers. We have a chat. Hello, everybody is saying hello today. So he made his tutorials to be able to use other renderers, but I was going to use only OpenGL, and that's why I removed all the virtual classes, and that's why we get the slight difference.
Functions that would be implemented by a class, a derived class such as OpenGL render API, and hypothetically Vulkan render API and whatever else, and it would sort of have the equivalent of these functions for a given render API. I mean, some of these
I'll never use like a Vulkan render API for my voxel engine. That's why I removed the virtuals for the functions.
things don't quite translate. Like, yes, you can have something like draw indexed being abstracted at that level where it wouldn't really make sense to take in this vertex array, which is a sort of an OpenGL only concept. It doesn't really exist in other render APIs. And pretty much all of these functions would need to take in a lot more context because OpenGL is this sort of global state machine, but the other render APIs are not. And that's one of the reasons, probably one of the biggest reasons why most rendering engineers prefer other APIs, not OpenGL. I think I can probably take the blame for that because the way that I chose to abstract a lot of these renderer operations, render API things in the game engine series was definitely much too fine-grained. A better example would be to look at something like modern day Hazel. And I'm not talking about Hazel 2D, the game engine series version of Hazel. I'm talking about like proper Hazel, the 3D version of the engine. So if we have a look at how this behavior, this dispatching of compute shaders and doing some synchronization, uploading, updating uniforms and everything between compute passes, how that's implemented in Hazel with all of Hazel's abstraction. Here inside the scene renderer, we have this light culling pass, which is a compute shader pass that is important to our forward plus renderer, which basically just determines which lights affect which pixels. Now you can see that we have a begin compute pass, a dispatch compute, and an end compute pass. The critical things to look at here are we have an actual compute pass, which is what we're beginning, and that sets up some base resources that are going to apply to every dispatch of that specific pass. So sometimes you'll write a compute shader and you want to dispatch it like, let's just say 100 times, but then you'll have so many resources that don't need to change dispatch to dispatch. They might change every pass or every frame. They might even never change. You might just bind them and that's it. You don't have to keep updating them. So those compute shader resources are set once essentially as part of the compute pass, and then things that actually get updated every dispatch are contained within a material. So we have two different places that we can store these resources, which in your case might be a uniform. They can be inside the pass and they can be inside the material. So this allows us to, for example, dispatch this a whole bunch of times and actually provide a different material every time. We could even update the material if we want and basically set, well, whatever we want. So there might be, this u underscore offset that you set. We might want to set that to a different vec3 between dispatches. And we can do that on the material like this and then dispatch using that appropriate material. But again, we can predefine these up front if we don't want to have any sort of GPU data transfer between these passes, which actually would be exactly what you would want in your case, because you can see that this offset uniform, for context, if we actually open up the compute shader, we'll be able to find it in here somewhere. U underscore, here it is, U underscore offset. So it's just a uniform vec3. So this U offset variable, which we end up using for determining which chunk we actually want to work on, that you can see is predefined to these values. This should probably be inside a for loop, by the way, with just an array defining all of these permutations. But anyway, you can see that this is not dynamic data that's being generated by our program. It's actually sort of a compile time constant that we can definitely determine up front. Now, things are a little bit different in OpenGL versus Vulkan because, for example, I mean, not really, to be honest, because you could just set this up to be, I mean, actually, the more I'm thinking about this, the more I'm thinking why this is not just an array that is inside the shader accessible at all times. I mean, you could make it a uniform buffer that you just set once, and that would be it. And then based on a certain index of the actual compute path.
If all the data I was sending was an array, I would still need to send to the compute shader like which part of the array to use. Like I will still have to send something, so it's not that big of a deal what he's.
You could just have it access the array, which would determine which offset data to actually use. So this entire system really doesn't have to be set up like this at all. But hypothetically, using that data, you could also create a whole array of like, I think there are 8 of these, right? Because we have 2 possible states across 3 variables. So 2 to the power of 3 gives us 8. So you could just have an array of 8 materials and then bind the appropriate one in a for loop, and that would have your uniform data there. However, again, in OpenGL, you would still have to upload that uniform float to the shader between draws, or rather between dispatches. So I would definitely just permanently store that data on the GPU somehow and then just access the appropriate offset, the appropriate index into an array of all of this data when you need to. And then when it comes to all of these barriers, things are a little bit more complicated when it comes to Vulkan, of course, and lower level APIs like DirectX 12 would be the same. In this case, Direct3D 12, we have these buffer memory barriers, which are part of the pipeline in this version of Hazel's rendering system, but that's basically how we make those happen. So how is this all abstracted? That was sort of the original question. Well, dispatch compute is a function inside the renderer. The way that I've set this up is the renderer is this class. It's a class really just for namespace purposes because everything in here is static, as you can see, and it has much higher level concepts than what you have over here inside this render command class. So it's actually kind of similar to this because, again, this is based off of my initial design, I guess, that I created for the game engine series. But you can see that this is much finer grained. This is much sort of lower level, which doesn't translate well to other APIs, with concepts like set viewport, which doesn't really make any sense, draw indexed, and set clear color clear. Instead of all that stuff, we have much higher level things like render static mesh. I mean, what does that mean? That does a whole bunch of things. We'll also have this compute pass API where we, for example, dispatch a compute shader. And then that's implemented by a specific render API. So for example, the Vulkan renderer will implement this function. And you can see that this is actual Vulkan code. But again, there's sort of a further abstraction here with Vulkan compute pass being a specific...
There's one thing he mentions in newer videos. He updated his engine to not be the one writing all of this code. He started using like an abstraction, like a library written from NVIDIA that abstracts away all the render APIs like OpenGL, Vulkan, etc. So I think that's an interesting update worth mentioning, because since he's now using a library that abstracts away the use of Vulkan, OpenGL, all the render libraries, a lot of the code is like just gone and deleted. He doesn't need to implement all these little finer details.
Version of that compute pass object. Vulkan compute pipeline being the Vulkan version of this compute pipeline abstraction, but we do actually end up calling actual Vulkan code over here. And then we do something like pipeline dispatch, which is in Vulkan compute pipeline. And then that is what does the VK command dispatch, which is equivalent to GL dispatch compute. Now, Hazel's backend render API, the way that we do that abstraction is actually changing. If you followed my channel this year and Hazel, you've probably heard of Renderer 2025. as I keep calling it. That's basically just changing the abstraction point so that instead of us inside Hazel having to implement each Render API, Renderer 2025 is us rewriting this abstraction of graphics APIs. Instead of us actually doing it ourselves within Hazel, we're outsourcing it to be done by a rendering hardware interface layer like NVRHI. I mean, in our case, it's specifically NVRHI, but creating an RHI is good. It's kind of what we're doing here. It's just that rather us doing that and spending our engineering resources on that, we can use an existing RHI that someone else, like NVIDIA in this case, has written, and they'll do the maintenance on that. But at the very least, it's already an existing RHI, which we can maintain going forward if we need to. It's a better starting point than doing this ourselves from scratch. In that newer version, what would happen is dispatch compute would then simply call into the renderer, which would have one implementation, and that would call into NVRHI to handle the abstraction internally within that NVRHI library. Now, the purpose of begin compute pass is to set up all of those resources. So if we have a look at what that actually does, we have sRender API begin compute pass, and again, inside the Vulkan renderer, what that will do is call pipeline begin, and then that's going to bind the actual pipeline, as well as bind the descriptor set. So this is what contains our resources that are pass wide that we want to use within our compute shader. It's going to bind them for the specific compute pass that we're trying to run. So hopefully that gives you a better idea of a higher level abstraction that would make more sense.
What this gave me as an idea is how complex his engine is. All these abstractions, everything he just said was so complex. Like, I don't know if I'll be ever writing something like that myself. Um, I prefer and I like to keep everything simple, and to like write messy code at first to get it working, then rewrite it with a lot of improvements. Like seeing his like complex code, I don't know if I'll be ever writing something like that.
Because that kind of API can exist within your voxel engine inside the renderer, inside your voxel engine, that will call into, say, OpenGL or NVRHI if you use that in the future and actually do that work there. Now, I will say that even though I've explained that sort of renderer side of things when it comes to abstracting all of this, you should really think about whether or not for this project, it's worth it, because abstracting a renderer like this into multiple render APIs is a lot of work, because aside from just mapping these functions, I mean, even if you use like an existing RHI like NVRHI that does that for you, it does certainly make things easier, but then you're also going to have to deal with shaders. How are your shaders going to get compiled? Because they have to be different for something like Vulkan versus DirectX. In that case, a common path would be to write your shader in HLSL and then compile it into SPIR-V for Vulkan.
I'm not worrying at all about this, where he mentions like what about other rendering APIs. I'll not be using other rendering APIs.
And either DXC or DXIL, depending on which version of Shrek 3D you're using. So the shader pipeline definitely gets a lot more complicated than something simple that you'll have here. And obviously, you've also heard me mention Vulkan and DirectX, whereas you're using OpenGL. So if you don't have any need to sort of go in that direction, I definitely wouldn't, unless you're trying to learn about it. Potentially, you just want to spend a little bit more time learning how engines work and graphics and rendering is interesting to you. That would be a good exercise, because you'll learn a lot more about how real engines handle multiple rendering APIs, which is important for the real world and for serious projects, but not for the fun of having all of these TNT explosions. You could just stick with one rendering API. If you need a little bit more control, a little bit more power potentially, and lower level control for things like performance, then you could use Vulkan. And that's obviously going to run on every desktop platform, as well as even some other platforms like mobile and a Nintendo Switch. And then you don't have to worry about this whole multiple render APIs thing with different shaders and different, it really becomes a big headache. Okay, so we've talked about the renderer abstraction. I think that that's probably a good place to leave it here for today. Here is that GL multi-draw arrays indirect function that he also mentioned in the email. And then, yeah, we just have a really simple GL draw arrays with points. So this is what draws the TNT count worth of points. So this is a big number, presumably. How many TNT to spawn? There it is, 10 million. So that's the default. Oh, by the way, you can add these like apostrophes between this to group these so that it's easier to read. So that's a little pro tip. But yeah, we have 10 million TNTs and they get spawned here. So we run to 10 million points, I'm assuming. I mean, the TNTs are going to die. So this is a constant though. So I'm not exactly sure how that would work because we probably shouldn't be rendering the initial quantity as a constant of TNTs. Is going to change. So that is
Here he's worried that the TNT count is always like 10 million, and it shouldn't be 10 million because TNTs explode and the count should change. But the reason I can always draw 10 million TNTs because I'm using a geometry shader, and here the primitive is GL points, not GL triangles. So I start off by just drawing 10 million points, and the geometry shader just checks for that particular point, which represents one TNT. It checks if that TNT is visible or not. If it's not visible, it just ignores that point. So every from the start, I always start with 10 million like TNT, but the geometry shader is the part. The geometry shader is the part where I actually regulate how many TNTs are being drawn. So to me, this is absolutely not a worry that TNT count is constant at 10 million. To me, this is not a worry. And another reason I left it like that as a constant to be 10 million is because I don't want to be like changing the structure of the data structure for the TNT, because you have to have somewhere the data for each TNT, like its velocity, its position. Each TNT has an ID. It knows where to look in that data structure of all the like data for each TNT. And if the TNT count was a variable and that made changes, it would have to I would have to add additional code and logic to calculate for every TNT now where it should look for its data. I wanted the data to be constant, to not have to change the data. And so one TNT, for example, has the ID of 100, and no matter what happens, no matter how many TNTs have exploded, that particular TNT will always look at its data with ID 100. Like all of this is just to overly simplify the whole process.
a bit weird. But anyway, this is where we will presumably render 10 million TNTs as points and then have the geometry shader expanded into actual geometry, into actual cubes, so that we can do that sort of process on the GPU. And then that specifically happens for the TNTs because here is where our terrain gets drawn. So yeah, there's lots of exciting stuff to look at here. Let me know what you guys want to see in the comment section below. Huge thank you to Pika CS or Pekka CS. I'm gonna go with Pika CS for sending in this beautiful project. If you guys want to send something in for me to take a look at, then send it into chernoreview@gmail.com. That email address and some instructions will be in the description below. Thank you all for watching. Till next time, goodbye.
Okay, we watched the video. We can finally start the project ourselves. We already saw it exploding a couple of times. We can see it one more time. This was 10 million TNT. This was so many TNT. And here is the result of all the explosions. You can remove terrain yourself with left clicking, and that's the whole like project. That's the whole project without like ambient occlusion. Um, let's like look at some parts of the code. Maybe we'll find something interesting. There's one more thing, like it supports texture, so we can try, for example, to change the texture. That's something we can do. Here we can use this Jolly Craft texture. So we should go here. Here is like my resources. We can back up this. Backup. It opened them. So I need access to all of these textures. So what you have to do is like go inside assets, Minecraft, textures, block. And here you would have to like find the textures, but maybe we can just like move all of them here. And now let's run the game to see if we are using the new texture. Yeah, and now we are using the new texture. This is Jollycraft. This is how easy it was to change the texture. The TNTs are different. And here, this is the new texture. Here, this is the stone. And this is the dirt blocks. And how the changing in texture works is it just looks for like these images, and using those images it creates one whole texture, the texture atlas, and that's what the game uses. It does it automatically. In my current Minecraft clone I have to create the texture atlas myself, this thing. And because I do it manually myself, that's why my current Minecraft clone, the Java one, doesn't support like texture packs. What's some interesting part of the code we can look at? Game layer. Something interesting that we can talk about. Maybe the compute shader. One thing about shaders is that they don't have includes. You don't have include for the textures. So what I mean by that is, for example, you create a structure. Here you create defines. You create a structure for the chunk, for example, how the chunk should look like. And because there are no includes, you would have to copy paste this everywhere. So I implemented an include myself here. I include the global source, which is this. So every shader has all of this information, so I don't have to type it all the time. This was really annoying. I think there is an extension for OpenGL that allows to include files, but it was just easier to implement it myself. What else can we look at? Clear explosions. Explode TNTs. Generate blocks. Yeah, I'm generating the terrain through the compute shaders as well. Everything's happening inside the compute shaders. So it's not even much OpenGL. It's mostly compute shaders. That's some interesting information. It's harder to see when I don't have like syntax highlighting. Um, I don't know how to have it in like Visual Studio. But so this file is generated blocks. Can I find the geometry shader? That's the most interesting part about this project. propagate explosions, draw terrain, TNT instance sync. I think this should be it. Yeah, geometry. This is the geometry shader. It accepts points and outputs triangle strip. And here it it looks at so the vertex shader actually, the vertex shader checks if it should draw that point. The vertex shader does the check and gives that information to the geometry shader. And now the geometry shader sees like if it should transform the point into a triangle strip, which is the TNT itself. So it's all done through this if conditional. So if this is true, it's going to transform it into a triangle strip. But if it's false, it will end the primitive. It will not continue the point into a triangle strip. This is why inside of the code I had the amount of TNTs as a constant, because the geometry shader is the one that's actually deciding how many TNTs to be drawn. And so here I create all the points for the triangle strip, also using the view projection, the transform, the center, and I just created all the points inside of the geometry shader. And then all of that goes through the fragment shader, which is like extremely simple. It just uses the texture and like some colors. Here I have the drawing of the terrain. And here we can see that even drawing the terrain, I have all the data is in the GPU. And so it was really efficient to draw everything that I need. I think I had vertex packing. I think I had that. Yeah, pack data. Like I had all kinds of optimizations and I've forgot most of them, since in my Java project I don't need those optimizations since I'm not going to explode 10 million TNT. But I pack the data so that in one integer you have most of the information you need. And here I extract that information, for example, the X, Y, and Z. All of that is extracted. And for example, you can pack like, instead of having X, Y, and Z, each of them be 32 bits, you can limit them, each one to be like 4 bits. And 4 bits for the positions was enough for me, since the terrain is quite limited in size. It's not like infinite terrain, so I didn't need to have that many positions. And here you can see how from the 0 to the like first 12 bits was the X, Y, and Z in the packed data. And then I have my normal ID. It's like 3 bits. And then my texture ID is like 4 bits. And I was able to afford to use just 4 bits for the texture ID, since I wasn't going to support that many block types. Here you can see we just have bedrock, dirt, grass, TNT, and that's it. So not that many, like 1, 2, 3, 4 block types. And here we have 4 bits of data, so like 2 to the power of 4. 4, 8, 16. So by packing the data efficiently, I had a limit of like having 16 blocks, which wasn't an issue for this particular project. And then I calculate my position. I calculate all my static lighting, my textures, my normals. And yeah, the fragment shader is extremely simple. We went through TNT instancing. Another shader is this is now a compute shader, the propagate explosions. Here we're propagating the explosions. And here is my queue that I was talking about. And you don't have data structures inside of shaders. So this queue is from here. It should be, it's just a structure, an array of nodes, and a node is another structure. We just have some information. So there isn't any queues. It's all abstracted just using arrays. My queue was an array and I needed a queue for like the BFS. So inside of the queue, I insert one node. Which node is this? This is to propagate an explosion. So I call this to propagate a particular explosion on X, Y, and Z. And it adds it in the queue as a node where I pack inside of it the position of the explosion, the chunk, and the explosion strength. And the logic here is much like how the lighting is propagated, like float fill. But instead of propagating a light level, I propagate an explosion level. And where do I save that data? So here I get the node, I unpack all the data. I set that the chunk should redraw since there's an explosion inside of this chunk, so this chunk should redraw, and possibly neighboring chunks should redraw as well. Block type, if it's a TNT block, then what does happen if it's a TNT block? I forgot most of it. Yeah, if it's not a bedrock, if the block type is different from a bedrock, we set its type to 0, which is like air. So this is how the explosion changes the terrain. So the explosion sets the block's type to 0, where the explosion has happened, and it sets the chunk should redraw. What else? Explosion value. If the explosion value is more than 1, it should continue the propagation, something like that. A for loop of 6, maybe this is the neighboring sites. Yeah, if explosion level is more than 1, it should propagate to its neighbors, and the neighbors are 6. So for each of the neighbors, it has to propagate that explosion. So I assume it should add inside of the queue a node. Yeah, here inside of the queue, I add a new node, which is the neighbor, and the explosion should be +1, explosion value. Oh, it's -1, yeah, it's -1, because at the center the explosion is the highest level, and at the end blocks, it's like the lowest level. So that's why it's -1. And here, when it reaches here and the explosion value is 1, it stops and doesn't continue propagating. And all of this was just one function that propagates an explosion. So this is not the start of the code. Here is the start of the code, the main function. And here we first check if the chunk has an explosion. If the chunk doesn't have an explosion, this saves us time to go through all the blocks. But if we know that the chunk has an explosion, we will go over all the blocks. And yeah, it's just a for loop where we go through all the blocks and we get the explosion value of that block. So we have the data for like each block. We like in the explosions array. Each block inside of explosions, I have to give the X, Y, and Z. That's how I get the explosion value. And if the explosion value is like TNT explosion strength, which is like 4. If it's like the explosion value is 4, there is an explosion there which we need to propagate. So basically, when you hit a TNT, and it explodes, when the TNT explodes, it will set a couple of things. When a TNT explodes, it will set that the chunk has an explosion, and for that particular block where there was an explosion, it sets the explosion value to 4. And this compute shader just goes over the chunk and looks for an explosion value of 4. And if it finds one, it propagates it. That's basically the code on a surface level. Here I update the TNT transforms. This is a compute shader again. Propagate explosions, we went through that. Generate quads, this again compute. Yeah, this compute shader, when we have to redraw a chunk, this compute shader will go over all the block types, and for each block type it will decide. It will generate the quads for rendering. Everything has been done in compute shaders. Generate blocks. What's this? Compute shader. Oh, frequency, amplitude, base height. So this should be terrain generation. Yeah, this should be terrain generation. And also, this is the code that generates the TNT placement. Yeah, here it sets the block type to TNT block, and it sets the stone blocks and dirt blocks. Explode TNT. Yeah, here when we have an explosion of a TNT, again a compute shader just sets what does it set? Yeah, it sets the explosion level to be like yeah, it sets the explosion level to be 4, the maximum. And here it's also setting the index of the TNT, so we know which is the owner of this explosion. And I forgot why I needed that. And here we said that this chunk has an explosion, so that the other passes will know that they should go over for this chunk through every block. And clear explosions goes over all the blocks and sets the explosion level to 0. And Is there anything else that would be interesting to go over? This is the update. This is just getting input. This is calling compute shader. This is for propagating the explosion. I'm calling the same compute shader for the propagation of explosions with an offset because um, because you cannot propagate an explosion for each chunk asynchronously at the same time, because when you have an explosion that's at the end of the chunk, it will go in the neighboring chunk, and this will cause a problem. And that's why I run the compute shader once, uh, and it will skip chunks. It will skip chunks so that it can run at the same time many chunks that are not direct neighbors, so that it's like because we will have the comfort of knowing that the compute shader will not like interfere with each other. But since I'm skipping chunks, I have to run the same code again, but with a different offset. And we have to do this a couple of times until we've gone through all the chunks. This is just to propagate the explosion. Here it is for playing sound. Then we update the TNT transforms, which is just to update the velocity, the positions, if it's visible. And then we clear all the explosions. And then we actually generate any quads if we have to do it. And here I had to do some synchronization, because if I didn't do this, like some chunks weren't rendering, they were missing. That was annoying. And here, I'm setting information for drawing later. Then rendering. Rendering is extremely simple. And yeah, that's it. I don't think there's anything more to go over. Yeah, that's it. So thank you for watching.